Integer value linear programming, or integer linear programming, is a category of optimization based on the idea that we're trying to solve variables that they are integers. They don't have real value, they just have integer values. Of course, we can mix these integers with other values. For example, having real values, we can call it an integer or mixed integer value programming. And the idea behind integer value mean programming is quite practical and useful, as many times, for example, if you're trying to optimizing the specific your production, so you always have to decide the variables to be an integer numbers. At the end, you always have a specific integer for the number of parts and so on. You will not have 1.5 parts or something like this. So it limits the program to solve the problem within an integer values. On the other hand, even for example, trying to schedule the people or machines, and for that you will say, like, I need hours, and sometimes 1.5 hours. Even for 1.5, you can break it down to actually solving for minutes, and 1.5 hours become 90 minutes. So this way you can always turn other problems into also integer value near linear programming. So in this class, what we're going to do is we're gonna define a problem, and then we will solve this problem by our hand, just to understand how these integer linear programming method works. So for start, we will first write some equations here that or a problem that we want to solve. So I have here written some problem. So what we need is to maximize. We have, let's say, 3x, we call it underscore 1 plus 2x, let's say underscore 2. So we need to maximize this values. This is our quest. Now we have some constraints. Let's say we have 2x1 plus x2 has to be less than or equal of 10. So this is one constraint. This is, as you can see, it's a linear constraint. At the end, this is a linear line. And as I said, many problems, especially non-engineering problems, or production scheduling, production, let's say, they decide the specific parts you want to produce. Production planning is also falls under this category of optimization. So we have these linear equations that can describe some kind of constraint. So x1 plus, say, x2 and less than or equal 8. We have x1, let's say we don't want it to be more than 4, and let's say x1 and I'll just make it more than or equals 0. X underscore 2 is also more than or equal to 0. That means it's all positive numbers. So we can see here, this is our problem we're trying to solve. Now, of course, the most important thing is this one. This is what we are trying to maximize. However, these constraints will kind of limit the areas in which we, the area in which we're trying to solve. And bear in mind also that this is all integers. So we have a specific numbers that we can look into it. At the end, the number of numbers exist between from 0 to 1 is quite infinity. You can have 0.01, 0.011, 0.0111, and so on. So having integers is a very big advantage. So let's try to, or let's solve this method by a method called a graphical, like the graphical method, in which we are actually mapping the area of solution based on these parameters, or based on these, the parameters and their constraints. So we start from x1 is more than or equal 0, and x2 is more than or equal 0. For that, let's have this contour line. Try and make it a bit bigger. And we have another contour line. Of course, this is a very graphical method, and this is why it's interesting and good for us to understand. So here we say this is, say it is, let's say x underscore, this is will be, and this will be x1, and this will be let's x2. So this line is x1, this line is x2, and what we want to do is, first we have these two. X1 is more than 0, x2 is also more than 0, and these two have been satisfied. So we can put them as let's say green, or it's a little bit, or just this blue. So here we can see x1 should be less than or equal 4. So in order to satisfy it, let's put this one a little bit maybe here. Just this is a little bit off the way. And we can say here, again, this is an integer, so we have to put these integers. Let's say 1, 2, 3, 4, 5, and so on. But actually just make it simple and just put it 4 here. So here is 4, and we know x1 is less than or equal 4. So let's have this one. We put a line that extends from here. Let's take this line and we can make it like this. So this line, and we can say that this is the location in which we are allowed to extend our solution. Also a little bit bigger or thicker line will be a good idea. So this is now x1 is less than or equal 4, has been satisfied. Now let's just give this one blue. Now here, so these two, let's say, have been satisfied. This one has been satisfied. This one we can just put them also black. Now x1 plus x2 is less than or equal 8. So how can we draw this line? First we try to put, or we already know it's a line. We take this equation and actually we remove this less, and we solve the equation of this one by having x1 equals 0, x2 is 8. So we know that when x1 is here, x2 has to be, say, here, going to be 8. And when x1, when x2, sorry, is 0, then x1 will be also 8. So it should be somewhere in here. So you can see that we can now draw a line that passes into these points. You can just give it, you know, like just put it green. No, green is not so obvious. So let's give it this purple number or purple color. So here we put a line. You can just take this line and it go from 8 to 8 and make it look beautiful. Now, where is this location? In order to know this location, actually there is a way to do it. Is we already know this one is 0, 0. So this location is here is going to be 0, 0. So at 0, 0, this part here, we say 0, 0, 0 plus 0, is it less than or equal 8? It is correct. That means the location located under this area. So it is you can just put it here. So the solution exists under this line and not here. So here will be off limit. Here we already have this line off limit. Here off limit and here within limit. So the intersection now is in this area. Now we go for the another one, which is the first one, and we can just make it red. And here 2x. Again, as we said, what we do is we put 2x1 plus x2 equal 10. And here we just remove the less and we equals 10. And then we put x2 is 0. So when x2 is 0, where is going to be x1? X1 will be 5. So x2 is going to be 0 here. X1 will be somewhere here. So it is going to be about here, which is 5. And again, like you can just make it simple here or like make it obvious. Now, x1, when it's 0, x2 will be 10. So it will be here. We just take the same thing in just this one. It's okay. Can just put it like this. And this one we just make it our color. And this you can see it should extend from 5 to 10. So something like this. And the location in which we are allowed to take is also going to be under here, because you just put 0, 0 in this equation, 0, 0, and it will be equals to 0. Is it less than 10? It's correct, it's less than 10. that means it makes it into this area. So the area we're looking into is actually this area. So the solution is going to be within that area. So in which this is the area. Like if we want to just put it, or just you can use this one. So this area is going to be our like interest area. Now bear in mind that now how can we solve it? We already know that x1 and x2 it should be an integer. So that means that the value of x1 and x2, it should be, for example, for x1 it should be 1, and then this line is going to be 2, and this line is going to be 3. These are the possible integers in this location. Just let's put them as this. Yeah. So these are the possible solution. Here also we can also assign them, or like limit the limited solution, which is, it used to be like from like 0, 1, 2, 3, 4, 5, 6 until we reach 8. This is the possible solution. So now how can we find these possible solutions? Well, the way we do that is basically we have to use this function, and as a beginning what we do is we give a reasonable value. It's of course this is a manual, and in actual program everything has to be done by software, but as a manual, as a graphical method, we give some estimation. So let's say we will start by having 6. So 6 makes x underscore 1 equals, now 6 when x2 is 0, x1, how much it will become? It will become 2, and in x or x2 x2 will be in this situation is going to be so x1 equals 0, 2x equals 6. That means it will be 3. So this number x1 equals 2 is actually going to be here, and we can give him a color. Let's say we already did this, and we already use a lot of red, so this kind of color. And here the other one should be 3, x2 equals, so this one going to be 3 is a bit too high here for this value, somehow here. So the line of this going to be this line, which extend, so just give it yeah, this way. So this is the first possible solution, and this is, we have to say that it happened at well, you can call it z equals 6. Now you try to do another one, which is of course you're trying to here maximize. So can we maximize it a bit? And the answer is yes, we can do. For example, if we put 12, then 12 x1, when this is 0, x1 will be 6, and actually 6 is not allowed, so 12 is a bit of limit. We said 9, but 9 is also off limit, so because it's a bit okay, let's put 12. 12 is a good number. Let's say x1 will be 12 under 3, it will be 4, and 12 x2, it will be 6. So this is the number. So the number will be, of course, this is going to be parallel, and here it will be x1 will be passing through 4. It's quite on the tip here, and x2 has to be 6. So somehow it should be like this. So here this has become z equal 12. Bear in mind, of course, you can pick other numbers in between, but we always limited with the integer. This is the main problem. So in when you have this as 4, this is quite the limit of this location. So you can move around here. Maybe you can see that when this line we keep increase it, it will go parallel and parallel until it will reach this point. And actually this point is the solution of this problem, because the contour line is just going to be going up linearly. So this is going to be the problem, the solution of this problem. Now here our solution going to be integer. However, there is another way to actually start from integer linear programming that is called relaxed integer linear programming, and this is basically a relaxed problem in which we can go from having an approximate number, like almost likely it will be about here, but it's not gonna reach here because here is not integer. So we take the most near integer, and then we leave the integer and we limit our search point around this initial integer solution. So this is exist. However, for this course for this lecture, we only care about integer values linear programming, and we will just take a solution that is going to be an integer, which is in this case about here, and the intersection between the integer of x1 and integer of x2 that is as close as possible to this point.